Hello, my amazing students. This is Mrs. A, and I love math. And today we're working on lesson 123 in your edition 2 Saxon Blue Book, and lesson 115 in your edition 3 Saxon Blue Book Algebra Half. And so today we're working on polygons and congruence. But there are so many vocabulary words that we have to learn that I decided the easiest thing to do will be to save the board for later when we actually do some practice problems. But we're going to work straight from the book here. Okay, here's the very first part we're going to look at. In mathematics, we call a flat surface a plane. A geometric figure drawn on a flat surface is called a planar figure. We remember that all mathematical lines are straight lines that have no ends. A part of a mathematical line is called a line segment. A polygon is a closed planar geometric figure whose sides are line segments. Okay, so we're going to see some examples of polygons here. Closed means that the line segments all connect and there are no openings, and planar means that the figure is flat and could be on a plane, a flat surface, and then geometric figure whose sides are line segments. So a polygon must have sides that are line segments. If a polygon has an indentation or a cave, it is called a concave polygon. If it does not have an indentation, it is called a convex polygon. Any 2 points in a convex polygon can be connected by a line that does not cross the boundary line of the polygon. So let's look at these. So this one here is not a polygon, and it's not a polygon because it has a rounded side. Polygons have only line segments. So that one is not a polygon because it has a rounded side. This one is not a polygon because it is not closed. Okay, it needs to be closed. You can think of this as a big fence, and there is an opening in the gate. Therefore, it is not a closed figure, and it is not a polygon. This one is a polygon because you can see that you can draw the whole polygon without lifting your finger, so it is closed. But it is concave. Do you see the little cave that goes in? So notice what they said. Here's point A inside the polygon, and here's point B inside the polygon. But you actually, in order to draw the line between A and B, you actually go outside the polygon. That tells you it is concave. Okay, it says if it is convex, all right, any 2 points in a convex polygon can be connected by a line that does not cross the boundary of the polygon. And in other words, it does not go outside the boundary of the polygon. So here is a convex polygon, and you're seeing any 2 points that we were to draw inside the polygon, we could connect with a line and never ever go outside of the polygon wall. Whereas concave, we could go outside the polygon wall to connect 2 points. So these are just very important definitions. Now, moving down a little bit, we're going to go to the bottom part here, which is just explaining those answers. Figure A is not a polygon because it has one side that is not straight. It has a curved part there, okay? Figure B is not a polygon because it is not closed. Figure C is a concave polygon, and figure D is a convex polygon. If all the angles in the convex polygon have equal measures and all of the sides have equal lengths, the polygon is called a regular polygon. Okay, so now they're moving into regular polygon, which we're going to see a lot of on the next page. But regular simply means that the polygon has all the same side lengths and all the same angles. Polygons are named according to the number of sides that they have. The polygon with the fewest number of sides is the triangle. A triangle is called an equilateral triangle, and we'll read the rest on the next page when I reposition this. Got my camera repositioned here for the next page. So now a triangle is an equilateral triangle if every angle in the triangle is 60 degrees. And a quadrilateral has 4 sides. So a triangle has 3 sides. A quadrilateral has 4 sides. And a regular quadrilateral, regular meaning it has all the same sides and all the same angles, a regular quadrilateral is a square. Okay, so it started talking about a triangle on the last page. 3 sides is a triangle. And then a regular triangle has all the sides the same and all the angles the same. So this is a regular or an equilateral triangle. A quadrilateral is a polygon that has 4 sides. And a regular quadrilateral is a square because it has all the same sides and all the 90-degree angles. All the sides are the same. We have already talked about the fact that a triangle always has 180 degrees, and that's why we have 60, 60, 60. 60 plus 60 plus 60 is 180, and so any regular triangle must have 180. And one thing we'll learn about quadrilaterals is that all of the angles must add up to 360 on a quadrilateral. So those are 2 rules we can always count on. And so a regular quadrilateral will have a 90, 90, 90, 90 because 4 times 90 is 360. So then we move on to talk about some more sides. So 5 sides is a pentagon, and then a regular pentagon will have all 5 sides the same length and all 5 angles the same size. Okay, a hexagon is going to have 6 sides. Now this one is a convex hexagon, isn't it? Because it's got, concave, excuse me, it's got a little cave. If I put a point here and a point here, then I would go outside. So that is a concave hexagon. And then a regular hexagon must be convex, and it will have all the same sides and all the same angles. So then it says, what do we do after we get done with pentagons and hexagons? Now, they're not drawing all of these figures because that would get very tedious to draw all of these, but they're defining them for you. A polygon with 7 sides is a heptagon. A polygon with 8 sides is an octagon. A polygon of 9 sides is a nonagon. And a polygon of 10 sides is a decagon. A polygon of 11 sides is an undecagon or an undecagon. Okay, and a polygon of 12 sides is a dodecagon. We note that there are no special names for polygons of more than 12 sides. When we speak of polygons of more than 12 sides, we use the word polygon and tell the number of sides or use the number of sides with the suffix gon. Thus, if a polygon has 143 sides, we would call it a polygon with 143 sides or a 143-gon. Okay, so 143-gon means it is a polygon with 43 sides. Wow, that's a lot of sides. Okay, so now we're moving down the page. A diagonal of a polygon is a line segment that connects 2 non-consecutive vertices. Now, non-consecutive means they're not right after each other. So we name the polygon by listing the vertices in order. These polygons are quadrilaterals MPRQ. MPRQ. Q, and AXCY, AXCY. When we name a quadrilateral, we always must name the vertices, which are the corner points, in order to define the polygon that we're speaking of. Now, the diagonals here also have names. So you see the lines are drawn here, the dashed lines here, that's a diagonal. And that diagonal could be called MR. Likewise, it could also be called RM. MR or RM would both describe, name that diagonal. This diagonal over here would be QP or PQ. Okay, so that's what it's telling you right here. Over here, we don't see the diagonals, but we could still name diagonal AC or CA, and we could name diagonal XY or YX. So, down here at the bottom, a trapezoid is a quadrilateral that has exactly two sides parallel. Here is a picture of a trapezoid. Okay, so two sides are parallel, but not the other two sides. Remember, parallel means that they run in exactly the same direction, the same slope of line. Okay, so a trapezoid is a quadrilateral that has exactly two parallel sides. A parallelogram is a quadrilateral that has two pairs of parallel sides. So these two sides run the same direction, and these two sides run the same direction. Okay, and then the sides that are parallel have the same length. So anytime you have two parallel sides in a parallelogram, they will have the same lengths. Like this is one hack, two hacks, two hacks. In these figures, equal tick marks denote equal lengths. Okay, now here we have a rectangle. A rectangle is a parallelogram that has also got the same measure. Here we've got right angles in a rectangle. Okay, so here a rectangle is a parallelogram in which all the angles have a measure of 90 degrees. A rhombus is a parallelogram that has four sides of equal length. So this is a rhombus. It has hack, 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 hack. All four sides are the same length. And it is a parallelogram, meaning that these two sides have the same slant and these two sides have the same slant. A square is a rhombus in which all angles have a measure of 90 degrees. So a parallelogram can turn into a rectangle if all the angles are 90 degrees. And a rhombus can turn into a square if all of the angles have 90 degrees. So we could say that all rectangles are parallelograms, but all parallelograms are not rectangles, because rectangle is more specific. And all squares are rhombuses, but all rhombuses are not squares. Okay, now this is a very interesting discussion of congruence. And this is how the author is moving into defining congruence for you. Consider this dialogue. Tom said, "Those two line segments are equal." Janice replied, "No, they are not. Only numbers can be equal. What you mean to say is that the number that describes the length of one segment equals the number that describes the length of the other segment." Tom then said, "But you will agree that those two triangles are equal." And Janice replied, "No, they are not. The numbers that describe the lengths of the sides of one triangle equal the numbers that describe the lengths of the sides of the other triangle. Also, the numbers that describe the measure of the angles opposite the pairs of equal sides are also equal. We use the word congruent to mean geometrically equal. Janice is correct because congruent means geometrically equal, except for position and orientation. If two geometric figures are congruent, That means that all corresponding measures of the figures are equal. Congruent is a term that is used often in geometry. In trigonometry and other branches of mathematics, we find it convenient to speak of equal sides and equal segments. When we do this, it is understood that we mean that the measures of the angles are equal and the lengths of the segments are equal. If two figures are congruent, we can place one figure over the other by sliding it over or rotating it or flipping it in some combination of these actions. If we slide the figure but do not rotate it, we call this a translation. If we flip a figure, it's called a reflection because the flipped figure looks like a mirror image. And they don't talk about a rotation except for right there. And a rotation is described right down here. Okay, so here we have translations. We have a figure. We have congruent figures that are just being slid to a different position. When we slide something to the different position, but we do not rotate it or flip it, we call that a translation. It's just a move, a slide. A rotation is when we spin a figure about a point, kind of like a fan here, isn't it? All right, so here's the center, and we are rotating it about that center point. And so all of these different positions would be rotations of the same triangle. So we would say, yes, the different triangles are congruent, but their different positions are rotations of the original. And then we have the same size figure. These are congruent triangles, but notice that they have been flipped over. They're mirror images of each other. That is called a reflection. All right, so we're going to be talking on the next page about how we get from one figure to another using either translation or rotation or reflection. So now we're going to move into our practice problems. You can see why I did this one showing you the book. This is a whole bunch of definitions and vocabulary. Okay, so all of the figures shown below are polygons. Figure A is also a quadrilateral, a rhombus, and a square. Give as many names as you can for each of the figures. So they've already done A for us. They told us A was a quadrilateral, that is 4 sides, and a rectangle, because a rectangle has right angles and opposite sides are parallel, okay, and the same length. And then it's also a rhombus, which is a smushed over regular, in other words, all the sides are the same. And then it is a square, which is more specific than anything, meaning all the sides are the same. And we have 90-degree angles. So we could describe that one figure 4 different ways. And they did that one for us. So now we're supposed to do the same thing for each of the others. So when we're looking at B, since all the sides are equal, we recognize that as a triangle, 3 sides. But it is, because all the sides are the same, it is a regular triangle. All the sides being the same forces all of the angles to also be the same, which means that we have a regular triangle, and a regular triangle has a specific name, which is equilateral triangle. So we have an equilateral triangle, and this one is a convex polygon. There's no cave, it's convex, so that's another name that we could call it. This one right here, C, is a trapezoid. And a trapezoid, remember, has only 2 sides that are parallel. This little arrow symbol here is our parallel line symbol. And it is also quadrilateral. It has 4 sides. And it is also a convex polygon. D, let's see if we can open it up so you can see it better. D has 4 sides, two pairs of parallel sides. So it is a parallelogram. D is also a rhombus because the side lengths are the same. It's a parallelogram with the same side length. That's a rhombus. And it is a quadrilateral. Okay, E is a rectangle. And they don't have the angles specified. So I don't know. We're just going to think that it is a true rectangle. We don't have the right angles in there. And we don't really have any markings. So I might have to rethink this one again. Since we have no markings showing that those are right angles, this angle could be like 89.5 degrees. And our eye would not be able to tell it, right? So it looks like a rectangle, but we don't have the markings to show that it's a rectangle. It could be a little bit off. So I think the best thing we can do with this one is just to say, hey, it's a quadrilateral that looks like a parallelogram and it looks like a rectangle, but we don't have any markings to say for sure, do we? So we would have to say, hey, it looks like a rectangle, but we can't prove that it is. Okay, what about this one? This one has the little parallelogram markings here. This is F, so it is a parallelogram. Opposite sides are parallel, and it is a quadrilateral, and that's the most we could really say about that, other than it is a convex polygon. This one right here is a concave polygon, and it has 1, 2, 3, 4, 5, 6 sides. So we could say it's a hexagon, but it is a concave hexagon, okay? And then we have this last one over here is 6-sided, and it is also showing that all of the angles are the same and all of the sides are the same. So it is a regular hexagon. Okay, so a regular hexagon is also a convex polygon. And now we'll move on to, okay, so this is our last part of this lesson. It says the pairs of figures shown below are congruent. Tell which movements are necessary to place figure A exactly on top of figure B. Okay, so now this one, they're showing you that these are the same. Okay, they say they are congruent figures, but their orientation is different. So remember, we have translations that simply move something, and then we have rotations, which will rotate about a point like a fan, and we have reflections, which will flip something over, okay, so that you get a mirror image of something. So if we looked at this one, let's just think, how could we get this one into this position? Okay, now if I were to drop this angle over, let me get a little pencil here. Okay, I decided this would be easiest if I went back to the board. So here we are. We have two shapes in our book on practice problem A, and we've got this triangle, and then the congruent triangle is over here, but it is in a different orientation. Okay, so what steps would we have to go through to get from here to here? Well, translation simply means to move something, and it's obvious that we're going to have to move this triangle over here. But even if we just slid this triangle over here, we would not be in the position of the other triangle. So we know we need a translation, but a translation is not enough. So what if we took the triangle and we rotated it? If we rotated it, it would be here, but guess what? The right angle is in the wrong place, isn't it? So even a rotation would not be enough. We are also going to have to flip it, which is a reflection. So for A, we need, going from here, we need a translation. We need a rotation to get it up there. But then we also need a flip, which is a reflection. So we need all three for A. Okay, so now let's do B. Okay, here's the B example or practice problem. So you can see that my triangle fits right here. And if I were just to flip it over like this, that's a flip, and then just slide it a little bit, then I would be on the other triangle. So this one is a move, which is a translation. We had to move it a little bit. Now, if they were right together, corner to corner, then we could just do a flip, which is a reflection. But there's a little bit of distance between them, and in your book, there's a lot of distance between them. So we would say this one is a flip and a translation, which is a move. So the flip is called a reflection. So we reflect and we translate. Okay, so this one is C, and you can see that we have our triangle, and it is exactly just slid over to meet the other one. So this is just a slide, no reflection or rotation necessary. Therefore, that one is just a translation. Okay, now look at these. I don't have any paper for these, so we're going to have to think a little bit. Now, if we just rotated this one around, if we rotated it, wouldn't the fat side be on the right? But over here, the fat side is on the left. Therefore, we're going to need a rotation and a flip, which is a reflection, and a slide, which is a translation. So this one is going to need all three to get to where it can lay on top of the other one. What about this last one down here? Letter M. Okay, can you see that if we picked a point of rotation, so suppose we just decided to rotate here on this point right here. If we rotated the whole thing around, picking this point to start with, then wouldn't it wind up being with this point downward? So on this last one, I would say rotation and translation would be enough. A flip is not necessary. Whew, that was a lot of definitions and vocabulary to learn, and we're done with that lesson. So that one was a long one, but hopefully you understand a lot more about geometric figures. And this is Mrs. A, and may God bless your day.